So welcome everyone. Good morning or good afternoon, depending on when you're watching this webinar. My name is Seve Cristoforo, and I am the Dissemination Task Leader for PoDIUM project, and I work for ICCS, the project coordinator that is based in Athens, Greece. This is the third and the final webinar in the PoDIUM Living Lab webinar series. And after exploring the German and the Spanish living labs of the project, today we turn our focus to the Italian living lab. And we're going to hear all about it from our partners that we have the pleasure to have here with us. Before I hand over to Guido, just a quick note from me. We have set aside some time for a discussion at the end of the presentations. Feel free to type in your comments at the Q&A box that you can find on your screen, your comments and questions, but we will take them all at the end after the presentations are over. Thank you again for joining us and for being here. And Guido, the floor is all yours.
Thank you, Sevi. And thank you to all participants for dropping in. It is a pleasure for me to present the Italian Living Lab and the use cases that we are working on for the PoDIUM project. We will present most of the challenges that we have implemented in the use cases and some preliminary results of this of the implementation. We will alternate some of my colleagues will alternate during this agenda. So we first will introduce the PoDIUM project and the Italian Living Lab, and then we will go through the details on the use case 4 and use case 5. Obviously, not all the details are can be explained in just 1 hour of a webinar, but we will try to give you a clear idea of what we have done, and we are very excited on the things we have implemented, and to show you the implementations and some of the results. Okay, just roughly speaking regarding the project, it's under the Horizon funding program, and it has the participation of 26 partners. The PoDIUM project stands for the PDI connectivity and cooperation enablers, building trust and sustainability for CCAM, which means that basically tries to enable CCAM applications by the use of information provided by the PDI, so the public data infrastructure. So infrastructure devices that or services that produce information usable by connected vehicles to enforce the mobility, and this is done through the MEC, the multi-axis edge computing, using also data fusion to enhance the quality of the information, as we will see on the trust and the truthfulness concepts. Also extend the standard messages. Also, the concept of integrity will be reviewed, and integration of vulnerable road users. We will see that in the Italian Living Lab, we have the privilege to have 2 types of use cases: one urban use case and a highway use case. This is the reference architecture of PoDIUM, which is a layered architecture. When we can see clearly that there is an edge intermediate layer where services for critical safety critical services might be located here in this edge layer because of the timing of the critical timing of the data flowing. There are also cloud applications in this project, and also a very wide set of road users that can participate, even connected or non-connected. So regarding the Italian Living Lab, as I said, one of the use cases, the use case 4, it deals with an urban scenario with vulnerable road users. So it's intended to protect vulnerable road users and to coordinate and help a vehicle, a connected vehicle, to pass a cross point, considering the vulnerable road users. It's located in Turin, and the use case 5, which is the risk management in a highway, and it's located in the Autostrada del Brennero. So let's start with the use case 4 in Turin. We will have the participation of some of our colleagues. We can say that in Turin, simplifying the use case is that we are trying to face the concept of cooperative perception, but a trusted cooperative perception. We will examine the concept of trust in the next slide. And Intersection Manoeuvre Assistance, which is the goal of this use case, and is one of the apps that we'll explain Svarco in the following slides. There are applications running on Mac in the edge layer, and basically the trust concept is that we are trying to get most of the information, even from vehicle sensors or from camera sensors on the fixed cameras and also LiDARs, in order to provide more reliable information, which is shared again to all road users, that can be used, for example, in this case, a connected automated vehicle to pass the cross point. So the concept of trust and truthfulness, there are two different things that sometimes they are confused, but the trust concept is that the data, the users producing data should be somehow at trustable sources. So basically what we have faced in this use case is that a user or an onboard unit or a roadside unit that produces information from their sensors is really who it is claiming to be. So that an onboard unit is really an identified onboard unit, and that it's their software, its software is integral, so that it hasn't had any hacker attacks that were mining the integrity of the software that originally was installed in the onboard unit, for example, or the roadside units. In the case of the truthfulness, it's another concept that deals with the fact that the information produced by those users is true or is more or less true, that a user might be producing information that may be not consistent with the other observations in other parts of the use case. So these are the two concepts that are faced in the use case. The deployment, all the partners have contributed with either with the cameras or the infrastructure, the communication infrastructure, the services, and the vehicle. And basically, this is a real photo of the cross point located in Turin, in Corso Spezia. And one of the maneuvers is depicted here in yellow line, and hypothetical vulnerable road user, which is crossing in the same time as the connected vehicle. So this is one of the scenarios that will be explained later. I will leave the floor to Fabrizio that will explain the enablers.
So sorry, I had my microphone muted. Thank you very much, Guido. Just a few words about me. My name is Fabrizio Gatti, and I have been working for 32 years in TIM, the former Telecom Italia, where after an articulated professional path within the innovation sector, I currently hold the position of project manager about company initiative related to smart mobility and autonomous and connected driving. So, let's move directly to the content of our presentation. It may seem obvious that team contribution within PoDIUM Italian Living Lab activities focuses mainly on the telecommunication aspects. And in this area, I could not begin the short talk by starting with 5G. 5G is the fifth generation of cellular network technology. And as an evolution of the previous wireless technologies, 5G was designed to provide better performances, mainly with focus on increasing bandwidth and reducing latency. What is really interesting is that the 3GPP, the body charged with drafting the technical standard for cellular telecommunication, had already introduced from 4G, that is the previous technology, the two basic areas of communication for the implementation of the V2X model, the vehicle to everything model, namely direct and long-range communication. In fact, two separate radio interfaces are used in this regard, and if short-range technology can be seen as an alternative to Wi-Fi-based systems such as the ATS-G5, in the second communication mode, the telecommunication world can make the most of those network features such as edge computing and network slicing, which allow for better implementation of a smart mobility application. Guido, could move. Okay, thank you. So, the communication architecture in the Italian Living Lab of PoDIUM can be represented as separated on three different levels, where various terminals of different natures, such as personal devices, vehicular devices, roadside units, etc., are dispersed across the territory and communicate with the world of application and function that are deployed or in the cloud, or when a very low latency is required, in the edge computing infrastructure made available by TIM. Next one, please. So, what is edge computing? Well, edge computing is an architectural solution enabling the availability of contents and application closer to the final customer in order to meet the requirements of latency mainly, but also security, resilience, and bandwidth, very, very strict. Edge computing allows also a more efficient distribution of computational capacity between devices and network. In the Italian Living Lab, MEC has a central role in use case 4 because it allows the fast information processing from road user. The application hosted by MEC fuse the data into a global environment model, digital twin, and use it to generate an efficient plan for the coordinated execution of cooperative driving maneuvers by sending recommendation for action to all road users involved. The TIM's MEC platform consists of two different logical entities. The first one is named Telco Edge Node, and the second one is named Service Edge Node. The Telco Edge Node is the entity responsible for separating the data traffic towards the application that are deployed on MEC infrastructure in order to allow the fast processing of this information. Why the service edge node is the environment where the application that are working on the MEC are deployed. Next slide, please.
Okay.
Okay, thank you. So I conclude this very brief speech saying very few words about the broker infrastructure. Well, what is Message Broker? Message Broker is a centralized resource that is shared by CV2X application that are used within the Italian Living Labs. The V2X application, namely the CV2X server, manage the service logic, the use case part, while the message broker manages the georouting of messages. In the case of PoDIUM, project message broker implement AMQP protocol that is a binary application layer protocol designed to efficiency support a wide variety of messaging application and communication partner. So that's all. Thank you very much to you for your attention.
Okay, regarding the platform involved in the use case 4, we can say that the digital twin is one of the components of the edge part. And it's based on the information received by the brokers. So even for use case 4 and use case 5, there is a broker underlying the digital twin on which the information arrives, the messages, the CATS messages, and then they are collected through Kafka and managed through in a pipeline on which most of the logics of the conversion or the signature checks are done. Also here we have implemented data truthfulness, which implements algorithms for the data fusion in order to get, for example, in this case, the cooperative perception messages are fused together with the sensor information received in order to consolidate more stable information regarding the vulnerable road users or other users detected and present in the cross point. And finally, the digital twin presents some APIs that are used by applications to access the information produced, such as the vulnerable road users, vulnerable road user aware intersection movement assistance application that will be explained later. And there is, for example, another application that we have implemented for this project, which is a visualizer, which I will show in the next slide. And also the risk management in the use case 5 is based on the digital twin and use the APIs present on the digital twin. This is our visualizer that is used for a live display of the cooperative perception messages. So all the objects detected on the cross point are introduced in the digital twin, and we have this real-time access to this information. It was useful in order to have a clear view on how the algorithms were working, and also for the experiments it's useful because so we know if everything is working or if the objects are rightly placed on the map. In fact, we used it to check the accuracy of the positions detected. We have found using a vulnerable road users with an RTK receiver and compared it with the detected with the detected information from the camera and LiDAR, and we had a precision of around less than 1 meter. So I think this is a proper result for the application. So regarding the vulnerable road user aware intersection movement assistance is the application that deals with this real-time information that you see here, and is in charge of Svarko, and I leave the floor to Svarko to explain it.
Thank you, Guido. Hello to everyone. I'm Alessio Coronel from Innovation Project Manager at Svarko. And here I'm presenting the demo. So to enhance pedestrian safety in the presence of autonomous vehicles and facilities coexistence, VIMA was developed. This service is designed to assess the potential for collision risk between the vehicle and pedestrians based on information received about the environment. Its core is therefore a risk management algorithm. For this use case, essentially input data for risk management, such as the vehicle's position and speed and the position of the VRU, were transmitted through CITS messages as CPM, CAM, SPOTM, and MAPM, which I'll explain later. Although the inputs defined for this use case are essential, VIMA is also capable of receiving additional types of input, allowing it to expand its functionality as needed. For instance, weather condition could serve as an additional input. Knowing whether it is raining, for example, could be linked to the extended braking times and potentially slower VRU movements. Such boundary conditions necessitate a higher safety margin, prompting adjustments to parameters to ensure safety even in non-standard scenarios. Data from vehicles, cameras, and LiDAR are transmitted to the digital twin, which aggregates and enhances the reliability of this information. Additionally, leveraging the digital twin enables the creation of a more dynamic digital infrastructure, one that can be easily expanded and updated with additional data as needed. This flexibility ensures significant scalability and adaptability, accommodating a wide range of requirements and interests. Regarding the structural inputs of the intersection, which are obtained through MAPM and SPOTM, we receive this data from 5T, a traffic operator in Turin. 5T gathers the necessary information via traffic management service. Once the data is received, VIMA processes it to determine whether a collision risk exists. If a risk is identified, an IVIM, so an in-vehicle information message, is generated, which serves as another sent to the vehicle via the AMQP broker queue. While the not yet, Guido, thank you. Yeah, no problem. While the message is directed to the vehicle as per the use case, VIMA's flexibility allows this alert to also be sent to pedestrians, cyclists, or other relevant parties as needed. To receive and transmit messages, Teams MAC will be utilized as it ensures minimal latency. This is essential for the system effective operation since we are considering security in a dynamic condition. Therefore, reaction times must be as short as possible. Next slide, please. Thank you. Going into detail about the logic on which VIMA is based, it has been divided into 3 steps. The first step is the acquisition of data and their mapping on the software. As previously mentioned, VIMA received the necessary data for the risk management from both the infrastructure and vehicle. This information is transmitted via CITS message, which include CAM, which contains the position and speed of the vehicle, CPM, which provides position and direction of travel of the VRU, SPOTM displays current and upcoming traffic light phases and their associated times. MAPM offers detailed information about the intersection in question, such as the size of the crosswalk, available lines, and potential vehicle trajectories, as is illustrated in the image. Once this data is collected, it's mapped within the software, and matchmaking occurs with the information in MAPM. The first step involves checking the coordinates of the vehicle and VRUs against those in the MAPM to ensure accurate geolocalization. Additionally, the distance between the vehicle and start of each lane is calculated, allowing the vehicle to be assigned to the nearest lane. The same approach is applied to the VRU. This process ensures that the possible trajectories are identified and all parties are related to the correct traffic light spaces. Next slide, please. The second step is the core of the service, the risk management algorithm. As previously mentioned, identifying the correct lanes is crucial for associating them with the appropriate traffic light cycle. This step is carried out during this phase of the service. The association is made using the information contained in the SPOTM, which provide details on the current and upcoming traffic light spaces along with the respective timings. Then the time required for the VRU to cross the road is calculated using the coordinates of their current position and the angle of travel. This allows the system to determine which side of the road the VRU is heading towards and how much distance remains to cover it. By assuming a constant walking speed of 1 meter per second, the estimated time for the VRU to complete the crossing is calculated. Both the pedestrian and the vehicle are assigned a virtual circumference, which is crucial for determining the potential collision risk. If the two circumferences intersect, as illustrated in the figure, a collision risk is declared between the vehicle and the VRU. The degree of intersection between the two circumferences directly correlates to the percentage of collision risk, indicating the likelihood of a collision occurring between the two. In situation where multiple pedestrians cross the road simultaneously, to prevent the vehicle from receiving multiple messages at once, VRUs that are crossing at close proximity are grouped together as a single VRU. This approach ensures that only one message is sent representing all the pedestrians in the area. Next slide, please. When VIMA detects a collision, the EVIM is generated and transmitted to the vehicle. If no risk is identified, no EVIM is sent. The EVIM contains information about the time it will take for the VRU to cross the road, which corresponds to the estimated time of the collision risk. Finally, the EVIM can have two states, new and updated. The new state occurs when VIMA identifies a collision risk with a specific VRU for the first time. The updated state is sent if VIMA confirms a collision with a risk of collision with a VRU that has already been considered, providing an update of the risk status. This update is particularly important in case where the pedestrian takes longer than the sample time to cross the road. In our case, this is crucial as the crossing is near an hospital, increasing the likelihood of encountering individuals with mobility impairments, which may slow their crossing time. Okay, I'm finished, and thank you all for listening to me.
Thank you, Alessio. It is time now to talk about the vehicle. So I leave the floor to Filippo from CRF.
Yeah. Thanks, Guido, for your kind introduction. My name is Filippo Visintainer. I'm fellow of V2X for ADAS and automated driving applications at Stellantis Software Engineering. I will outline what is the application from the perspective of the connected and automated vehicle. So we are talking here of a so-called Day 2 V2X application. Day 1 applications are for warning only. Here we are talking about sensing driving. So the concept is to use V2X as an additional sensor. The vehicle in here in PoDIUM receives trusted and highly reliable data about vulnerable road users, pedestrians, cyclists at the crossroads. The in-vehicle application combines vehicle dynamics, its own sensors, and the V2X messages received to assist the driver or the autonomous driving. We have three main benefits: an improved awareness of the surrounding objects at the crossroads, especially vulnerable road users that are not seen by the onboard sensors due to the field of view that is hindered, for instance, by other cars. We have the benefit of a preventive warning, so ensuring safety margins. For instance, if a VURU violates its red light. And also, thanks to the so-called VIMA application, we have heard about this new acronym, so VURU Intersection Movement Assist Application. In perspective, an automated vehicle could be given the actual time slot where it's safe to cross the intersection. So it's not only important in an urban scenario to receive the green light from the traffic light, but to be assisted by an application that knows everything that is dynamically changing all the road users in the intersection to safely indicate the vehicle when it's really safe to cross the intersection. So manage the priorities. These applications have been developed on board on a vehicle prototype in Orbassano, Stellantis CRF premises, integrating on the trunk of the vehicle prototyping units such as the V2X onboard unit by Lynx, provided by Lynx, a main PoDIUM electronic control unit where the data fusion between the sensors and V2X are performed thanks to applications developed by Stellantis CRF. And these are the core elements that give the assistance. You see the PoDIUM display on the left. It gives assistance to the driver, potentially also to the automated driving function. So the vehicle is equipped also with an automated driving electronic control unit, but in urban scenarios, in the free flow conditions, we are testing it in terms just of perception and recommendation to the driver. Next slide, please. Yes. So our R&D in PoDIUM focuses on the V2X data. The data exchange, in particular, for use case, this urban use case 4, is with the infrastructure to get messages about the traffic light, the road geometry, the vulnerable road users, but also hazard warning of violations. So you get both the collective perception message, so what is detected, for instance, from the cameras and stored into the digital twin, but you get also information about sudden crossing in forms of notifications. And of course, the messages regarding the state of clearance of the road, whether the zebra crossing is clear or not, thanks to the in-vehicle information messages that Alessio was mentioned before. And in turn, the car sends its positions and detected objects, so other vehicles or vulnerable road users, to the PoDIUM infrastructure. In terms of cooperative awareness message, that is the presence of the vehicle itself, is sent through CAMs to the infrastructure, and also in terms of collective perception. So the vehicle detects objects such as other vehicles or vulnerable road users and sends it to the PoDIUM infrastructure, thus contributing as a vehicle itself to the collective perception. All this is exchanged mainly through the 5G communication, but PC5 and ITS-G5 short-range communications are also available. V2X onboard unit gets the message from the infrastructure and filters the most relevant messages in terms of V2X objects and sends them over the controller area network to the PoDIUM PC that hosts the application. In turn, the PoDIUM PC sends the data sensed by the vehicle to the V2X onboard unit that sends the collective perception message and CAM message to the PoDIUM infrastructure. So I want the public to focus really on this bidirectional data exchange that is key of a cooperative system. Next, please. We are addressing this in three main scenarios: the crossing straight, so the vehicle goes straight at the crossroad, the vehicle turns right, or the vehicle turns left. And within these scenarios, specific sub cases, let's say, are defined based on VRU behavior. So the VRU could be standstill, so it should not give any particular warning or recommendation. It could be a false alarm if we gave a warning to the vehicle or the driver. Or the VRU may be crossing in violation of the red, or the VRU may be crossing with an ordinary crossing with a green light, whereby the VIMA gives precedence to the VRU and then to the vehicle, etc., etc. All these sub-scenarios are being tested in the Living Lab. Next. In order to check what is happening, and as a let's say, development of what could be a possible user interface, we have developed in our prototyping environment this HMI. So you have a virtual driving scene that in the screen, the black screen, you see with a map. The green box is the host vehicle, so the ego vehicle. You see a blue box that is for example, a sensed vehicle from onboard sensors, and the red box in the boxes in red on the right represent the vulnerable road users that are perceived via the collective perception message. So these vulnerable road users in the screenshot in particular are the ones not sensed by the vehicle sensors, but received from the PoDIUM infrastructure as vulnerable road users on that intersection. We have in the upper part of the screen a recommendation that is given, in this case to pay attention. It could be a recommendation also to slow down, along with the crossing time of the pedestrian. Of course, this is not a final HMI, it's just a proof of concept to check that we can actually monitor the state of clearance of the zebra crossing and give recommendation to the driver or potentially to the automated driving function. You see a gray representation of a VRU warning. It is gray if no notification of, for example, sudden crossing of violation is received. But if there is a violation of the pedestrian or a sudden crossing, this warning, VRU warning on the right, gets colored, and it means that it means practically an emergency situation, because there is no precedence management by the PoDIUM infrastructure. It's just a notification that an exceptional event happens. Okay, so that the VIMA cannot handle the priorities, just warns the vehicle. Next, please. Where we are in terms of testing, we have done successfully the functional testing, and we have started to analyze the experimental results. Here are gross, let's say, let me call gross analysis of the first experimental data. Why gross and not detailed? Because there have been some debugging phases, so not all detections are comparable in terms of accuracy, so that we could merge all the validation tests carried out, for example, in this case, it's 10 trials on a specific sub-scenario of a right turn, in order to retrieve the first inference of what could be the potential. And here we already inferred that there is a great potential in this collective perception. So the vehicle in all these test trials was moving in a free flow, free traffic scenarios. It's in the center of Turin, so there were a lot of cars, and not always the onboard sensors detect the pedestrian. Here you see, for example, a mapping of the detected objects in function of the distance of the ego vehicle to the intersection, and not always could the pedestrian be seen by the onboard sensors, due to the fact, for instance, that we had a car in front or a parked car besides, etc., etc. While every time, or almost every time, we received the collective perception message. So during the whole approach to the intersection, could the vehicle be assisted from the PoDIUM infrastructure by receiving the pedestrians that were crossing the intersection. It is to be noticed that here it's not just every pedestrian that is detected at this busy crossroads, but it's the pedestrian deemed relevant for the vehicle, because here we monitor the objects that were sent by the links onboard unit through the controller area network bus to the in-vehicle functionality. So really the useful pedestrian for our crossing maneuver. Thanks. Next slide. What is the state of play of PoDIUM use case 4? So the onboard system functionalities has been verified in more than 40 test runs, because in the previous slides I showed just one of the sub cases, but overall we had 6 sub cases. So in total 40 test runs. There is, as I said, improvement of ongoing before we can evaluate the system. Improvement on the lane level positioning of the ego car. And then there is the final PoDIUM infrastructure integration into Team Mech. So there will be a fine-tuning in the overall system before we measure, let's say, the use cases in its final configuration and derive the performance indicators. What performance indicators are we addressing? Of course, the reliability of the detection of a vulnerable road user that is in conflict with the vehicle, especially from OEMs. We are very scared of possible false positives, but also false negatives. The vehicle positioning, lane level confidence of the vehicle positioning is key in order to assess that the vehicle is actually crossing and what is the trajectory conflict. We will also try to understand whether the maneuver assisted by this VIMA application are actually maneuvers that resemble a realistic behavior of the driver at the intersection, or for instance, if the time to cross is too long, etc., etc. So also the speed profile of the maneuver will be measured and taken into account. And finally, as it is in all cooperative systems, one of the key performance indicators is the latency of information, and in general, the latency of processing from the infrastructure detection of the vulnerable road users to the recommendation given to the vehicle driver or automated driving function. Thanks.
Okay, regarding the onboard units participating in the use case 4, we can say that the onboard unit provided by Lynx is a research-driven device which has been integrated in Lynx from off-the-shelf components. It has a GPU just for other kinds of applications, but they are also used in the roadside units because the embedded architecture is the same for both components. And it provides the connectivity, 5G connectivity, and short-range connectivity, and also connectivity within the vehicle with CAN bus, which is the main interface with the vehicle, where it transmits the consumed messages coming from the broker and from the other services, also from the received in short range. And the Ethernet interface, which is used for debugging purposes with other external entities, and Wi-Fi hotspot for eventually other applications. A particular feature of the onboard units is that we have a preliminary dead reckoning fix that we have been testing on these onboard units, and we have this precision using the dead reckoning and RTK corrections. Okay, regarding the services implemented in the onboard units, there is a stack developed by Links and containerized inside, so it allows to be updated. So this is somehow flexible for research purposes, so we can do modifications on the fly and for the experiments. The stack can understand the relevance of a message, because we can receive many messages, but only a few might be interesting for the vehicle. So only the traffic light, which is in front of the vehicle, is interesting to the vehicle, and only the objects detected in front of the vehicle are important to the vehicle. So the messages are filtered on this stack, and the messages that can be consumed are the standard messages, then IV messages, SPAT, map, and also it can decode the CPMs and also BAMs from vulnerable road users. Another kind of onboard unit is the VRU application, which is a smartphone application, a 5G smartphone application that we have been implementing on this time. And some of the features we have tested are the decodification of the SPAT map and all the standard messages. And it allows the user to navigate, just in the video that I will show. We can use it as an onboard unit for a pedestrian or an onboard unit for a bicycle. So it's possible to choose one of the two use cases. And also it can use the precise positioning hardware, which is installed on the bicycle for implemented for the project. So we can see here that the application can allows the user to navigate, and this functionality allows also to publish the future route of the pedestrian. So it's an additional information that is used in the risk in the calculation of the risk. So we can transmit this information, and also the live information coming from standard messages such as the name or SPATM. As you saw here in the video, there are also the traffic lights with the remaining time for the traffic light to change. Regarding the trust computing, as we said before, the two concepts of trustworthiness and truthfulness of the information managed in the use case 4, we deal in particular the trust of the information by trusting the nodes that produce data. In our cases is the onboard unit, which is equipped with the TPM that allows the low level system to be checked periodically at boot time and periodically in order to assure that all the components, well known as sealed objects inside the box, are integral, so they are not changed during the time, and they haven't they haven't had any attacks, cybernetic attacks to modify the code or the configuration files. So periodically there is an attester or verifier that controls and checks the integrity of this of all the components, and the TPM participates in the process. So this is the concept of a trust computing basis. So an onboard unit behaves as a trust computing basis, and as a result, there is software produced by Links, which has been named under the acronym EMBRAVE, that it's embedded remote attestation and verification framework, which is a software that implements the agents on the onboard units and also the verifiers on the edge of the network. So there might be more than one verifier, and obviously there are many agents that are claiming to be verified. So in this case, the attester, so the onboard units, join to the service in order to be verified by one verifier, and the verifier is assigned to an onboard unit and periodically starts the verification process, and publish the verification result in a broker, in MQTT, and this makes the result publicly, well, not publicly, but securely available in a trusted domain on which the AMQP broker belongs. So this is the mechanism through we can notify the broker that a user has been verified, a number unit has been verified or not verified, and depending on this result, it is authorized or not in the broker to transmit packets, and being allowed to use the information on the published on the broker. Okay, this is the last part of the regarding the use case 4. Let's shift to the use case 5, which is regarding the A22 tunnel, or the risk management in a highway tunnel. So I leave the floor to Paolo and A22 partners to present. Welcome, Paolo.
Thank you, Guido. I am Paolo Faccina. I'm the CITS manager for Autostrada del Brennero, which is a highway road operator. The aim of this presentation is to show you the use case 5 setup and why it's important for highway scenarios. We manage a very long and complex infrastructure, which is part of the Scandinavian Mediterranean corridor, and it's one of the most important connections between Northern and Southern Europe. So we are subjected to a very heavy traffic flow of daily vehicles with an increasing trend. So we are reaching maximum capacity. This, coupled with the fact that we have a very complex topologies with viaducts, bridges, tunnels, that makes intervention on site challenging. This makes prevention and safety very important objectives, either for the human cost that they entails, and either for the fact that any accident could paralyze the entire infrastructures. Next. So, of all places along the highway, which is one of the most dangerous one? Of course, roadworks, but luckily they are not always present. In this case, we are talking about tunnels. Why? This is because when a driver encounters a piece of the road where is the tunnel, it has reduced visibility. There could be potential hazard, and also it will be enter a confined space with no way out, no easy way out. This, add with the transition between natural and artificial light, could raise the risk level, and it impacts safety. So the aim for this use case is to develop a system that can assess in real time the risk levels of a tunnel and provide timely guidance to automated vehicles. This is a scenario. This setup is quite common in our highways in the north part, because we have a lot of unidirectional tunnels, and a lot of them are very long, exceeding 800 meters. So it's a very long stretch of road where there could be potential hazards. Can you next? How we plan to warn the drivers? By generating appropriate danger message. So approaching automatic vehicles can receive dynamic alerts and decide to engage or disengage cooperative adaptive cruise control or perform cooperative perception by exchanging CPM messages with the nearby vehicles. What makes this scenario unique? Tackling the vehicle position issues by using a position solution to give continuous position before, during, and after the tunnel. Why this is important? Because accurate self-localization through onboard data fusion enables, first and foremost, the continuous provision of CATA service, and second, it enables automation level operation. To achieve that results, we split our implementation into directions, addressing different aspects. The first one is the risk assessment computation, message generation and broadcasting. And the second one is the positioning solution to improve the position accuracy of the automated vehicles with the aim to reach lane level precision. These two parts can then be combined together in a tunnel setup. Next. Let's start for the risk assessment part. We have chosen a pilot site which is the tunnel of Tush, located north of Bolzano. It's a 300 meters long tunnel, and has already the infrastructure that allows us to set up any equipment needed for the risk assessment module. Because, as I said at the beginning, we are subjected to very heavy traffic flow, so we have to manage carefully road closure and road intervention to install sensor along the highway. Next. What will be installed in each entrance of the tunnels on top of the VMS panel signal? Each tunnel entrance will be equipped with a sensor developed by our partner Lynx, which consists of a camera, a LiDAR sensor, a roadside unit, which hosts a GPU to use AI-based algorithms, and it is able to communicate with using different protocols, which is the 5G, the HCG5, and also the wired communication. The first point I want to stress is that, of course, any equipment that will be installed in a highway setup needs to guarantee high availability. And this setup has been installed already for the use case 4, similar one, and they've been up and running continuously with ones outdoors, only connected to power. So this is a setup that gives you availability and reliability. Next slide is show a little video who show how the algorithm counting vehicles entering and exiting the tunnel works. And also there is an improvement of this counting algorithm, which classifies the vehicles between light and heavy one, and is able to recognize if a particular heavy vehicle is carrying dangerous goods. Who are the actors involved in the risk assessment components? We have the input sources, which are the CITS system, which is outside of PoDIUM, is a tool we already developed in other European projects like C-Roads, and which publish events that are controlled by the traffic control centers. This is a one input source to assess, to help the system to assess the risk level. The second input source are the roadside units, which are on site, and they're able to collect all the CAMs and CPM messages broadcasted by the car and get the data from all the sensors attached to them. They encode and send this information, which goes to the digital twin along with the message published by the CITS system. The digital twins fuses all the messages together and store them, and then send this aggregate data to the risk management module, which updates the counts and perform a risk assessment, and then provide a refined warning danger message to the connected vehicles, which can receive them, analyze them, and then the drivers could adapt the behavior, or the automatic driving system can adapt the behavior of the car. Next. How does it work? All the risk assessment flow. The first step is data collection. I have to get as many data as possible for road side sensor and automatic vehicles. Then there is the complex part, which is the risk assessment level, because I have to analyze traffic density, speed, road condition, number of vehicles, type of the good carried by the vehicles to determine a risk level. Then I have to notify this risk assessment to the automatic vehicle in real time. And then they have to adapt the behavior. And underlying all that, there is a continuous monitoring. So I have to dynamically update the risk level as the new data is received. So in this way, automatic vehicles can receive crucial risk information for safe navigation in tunnels. The best part of this system is that it's tunnel independent. It can be potentially extended in any problematic piece of road, like places with the sharp ends, or a particular stretch of road which has a high level of accident. You can use this system to provide better guidance for drivers. Next. In the realm of cooperative message system, there are a lot of information exchanges between vehicles and infrastructure, and between vehicles to vehicles. For assistant and autonomous driving, this information exchange must meet strict constraint on reliability and safety. The risk assessment part is in charge of the message requirement, which states that the message has to be truthful, in real time, and has to be correctly localized. The problem now lies on the receiver side, because to correctly interpret the message, drivers needs to know its exact position. That's why we are interested in the tunnel environment, because in these places there are GPS issues. Next. As I said, without precise position, information becomes unreliable, leading to flawed risk assessment and a safe perception of danger. Why it happens in tunnels? That's because you have a reduced satellite visibility, you have a reflection of absorption of the signal, or in the worst case scenario, you don't have signal. So in both cases, when you have a low precision on GPS or no GPS signal, the autonomous driving face challenges, because in the first case, with the weak signal, the car does not know precisely where it is, so it can interpret the wrong relevant message on its driving path. And the other one, if it doesn't know its position, it cannot determine whether the message is relevant for them or not. So this has as consequence safety risk, because what I said. To address these issues, we integrate in our scenarios a part specifically designed to help automatic vehicles to improve assessment of their location. This tool, along with other sources like, for example, odometry, can help to mitigate the problem of GPS loss. The positioning solution we decided to test is a V2X locate, which is a vendor specific. We choose it as an option since all our roadside unit and onboard unit involved in our test case were of the same vendor. This means that this system must be installed in both sender and receiver side. This system exchanges specific ETSI messages, broadcasting the exact position of their RSU to the onboard units, and uses round time trip and three-dimensional trilateration algorithm to give improved positioning. To be able to give significant information, an onboard tuning must be in a radius of at least 3 RSU at any given time inside of the tunnel. We know from vendor specification that this system has good latitudinal accuracy, but has some lateral limitation in tunnels. To determine the optimal configuration of roadside units which can optimize the lateral accuracy, many configurations need to be tested, varying RSU density, location, and distance. The aim, of course, is to get as close as possible to lane precision level. Next one. The system, the V2X locate system, is thought to be used as a static fixed field disposition. But since we have many constraints over the works that can be done in our tunnels due to heavy traffic flow, and we need to test many configurations to reach the optimal one, we develop a mobile solution of the system. This solution can be deployed anywhere and easily moved to help study its performance. I have to stress that the V2X locate, even in the fixed position and of course in the mobile solution, has very stringent requirement over the positioning and the configuration of the roadside units. Latitude, longitude, and altitude must set precisely on the RSU side. And the field placement of the equipment allows only a margin of error of at most 5 centimeters between the setting on the location and the position which the RSU is broadcasting. We prepare 10 mobile stations to do that with a POA battery charger to allow extended test trials. We did some field tests. Our partner from Stellantis will go deeper on the driver perspective of that. With this, I'm finished presentation on the setup, and I give you the floor to my partner. Thank you for your attention.
Thanks, Paolo. Perfect introduction to what is experienced in the connected and automated vehicle. Next slide. Okay, so we are talking again of V2X in support of day 2 functionalities, so sensing driving. In this case, in the highway, Stellantis CRF has been addressing cooperative adaptive cruise control. So V2X in support of the cruise control of the vehicle. And also day 3 experimental application is about V2X enabling to keep the highly automated driving operation. So thanks to V2X collective perception, in particular here V2V collective perception, a vehicle following another vehicle and the other vehicle ahead exchanging information about the detected object extends the event horizon, thus enabling a safety margin for level 4 automated driving. We have been demonstrating this in the Autobrennero corridor since 2019 in the 5G Carmen project. PoDIUM leveraged on the 5G Carmen Open Sky results about these applications, adding the tunnel. So in this case, the PoDIUM added value with respect to Stellantis CRF R&D on this topic is the physical digital infrastructure at tunnels. And this physical digital infrastructure has got 2 roles. One is the V2I aid to inform risky condition, roadworks and local hazards. So previously we had, for example, tested cooperative ACC, but without the roadworks. In PoDIUM we test it with the lane closure, for instance, due to roadworks warning. And the other aspect regards the tunnel. So previously we hadn't tested these functionalities in a GNSS denied environment such as a tunnel, and also the positioning solutions that can be provided within the tunnel from the infrastructure. For instance, as Paolo mentioned, the V2X signals that enable a trilateration, thus to infer the vehicle position within the tunnel. And also, as CRF Stellantis, we have developed a dead reckoning solution based on our vehicle sensors and HD maps. Next, please. So in speeding up a bit here, we analogously to use case 4, we have developed here 2 vehicle prototypes that have been set up with the PoDIUM main PC and the communication unit. In addition, in use case 5, we focus on submeter positioning, not only outside in open sky with precise GNSS and RTK correction, which is for us state of the art, but also with this novel dead reckoning solution developed in PoDIUM, and also the V2X positioning based on trilateration, because we have to have also the onboard unit dedicated to this trilateration-based positioning on board the car, not only on the roadside limits. So the cooperative adaptive cruise control works based on the V2V cooperative messages between the vehicles, and also V2I and V2N messages with the infrastructure, that the infrastructure practically gives a digital representation of the roadworks, for instance, and inside the roadworks that are represented by a notification message, DEM, there is the speed limit that the vehicle, cooperative HCC, follows as a new target for the vehicle control. So the user set speed, for instance, 130 gets decreased within the roadworks area to the speed limit set by the roadworks, which is lower than the legal one. Automation level 4 is based on the CPM. Onboard system overview, very quickly, it's similar to the previous one. We have a communication unit, a PoDIUM PC that gets the relevant messages, and based on that has the cooperative applications. And here, in addition, with respect to use case 4, we not only give a recommendation as a proof of concept in use case 4, but here we do also the actuation in longitudinal control. So the vehicles along the A22 motorway can also actuate, so control the vehicle longitudinally based on V2X information. In addition, as you see on the left, there are dedicated modules to receive the position and also position the vehicle also within the tunnel. Next, please. So the driving scenarios are, again, CACC in all its configurations, CACC, engagement, disengagement based on the road closure, etc. Next slide. I'm trying to accelerate to leave room for questions. And level 4 operational design domain. Here, just a few words on level 4. So level 4 deals with the system being able to react also on exceptional condition. So the concept is that the vehicle can go level 4 if it's following another vehicle on the highway, and the vehicle in front sends cooperative detections to the vehicle in the back, so that the vehicle in the back knows that if the vehicle in front is communicating the detections in front of itself, it can shield our ego vehicle from exceptional event. If there comes a third car in between that is not connected or not part of this collective perception, so it is an external car and merges, it causes an exit of the level 4 operational design domain. So the vehicle cannot go level 4 anymore if there is a cut-in of a third car. Next, please. So we have done, where are we? We have done the first functional tests on some tunnels in order to understand whether we can keep the level 4 automated driving, whether we can run the different scenarios. Here you see, for instance, a car with CACC, so following another cooperative car, and also the cooperative car in front sends the detections. So the EGO vehicle is in level 4 automated driving, not actually running automatically on the public highway, but it has got level 4 perception and ODD indication, so operational design domain indication. As in tunnel, the car can keep in this level 4 operational design domain perception. So it can keep in safe condition as long as the car in front is tracked, as long as the EGO vehicle positioning is good, and as long as there is no car, no external car in between, cutting in between the two cars that proceed in this car follow situation. As soon as another car does the cut-in, for example, a car which is not equipped by V2X, the onboard system realizes that the car being followed is not the cooperative car, so it exits the level 4 operational design domain. But since the precise positioning is still working, it can keep level 3 automated driving. Level 3 automated driving decays as soon as the positioning is lost within the tunnel. And as a matter of fact, we have experienced that thanks to our advanced dead reckoning solution developed in PoDIUM, the level 3 needed lane level positioning can be kept in tunnels, at least in tunnels up to almost 1 kilometer. The campaign is ongoing. Next. What we are doing here is a preliminary road testing in GNSS denied environment, but since A22 is waiting to install it on a closed part, a tunnel or similar, we have started to test it in a test track by artificially disabling the GPS. So here the vehicle is not receiving the GPS position, but it's working on self-localization plus this V2X locate. So this V2X relative positioning based on trilateration. Here we could do through the data fusion between dead reckoning and V2X locate, we could correctly perform the scenarios of a cooperative ACC with roadworks warning, even in GNSS denied environment. Next slide. Okay, where are we? So there have been several tests, almost 48 times of test runs with scenarios in Trento and Bolzano. The functional testing has been practically ended. The scenarios work correctly, but while the onboard data fusion of dead reckoning, so HD maps and lane detections can work and position the vehicle correctly 100% of the times, even in tunnels, etc. Without the infrastructure support, V2X is lost roughly after 500 meters. So for that's our first measurement. That's 15 to 40 seconds from the tunnel entrance. So for short tunnels, we keep every time the V2X. For a longer tunnel, we lose the V2X functionality. It can be due to two kind of reasons. One is some GPS signals that is used by the V2X software inside the vehicle, so that when the fix is lost, the V2X functionality is lost as well. But also it can be due to the timing synchronization of the units used for communicating. So we are investigating on this effect. trilateration-based positioning works correctly, but the performance needs to be optimized. We performed the first functional tests on trilateration-based positioning I presented in the previous slides, and overall the scenarios worked, but actually it was mainly because our dead reckoning solution of relative positioning based on HT map and lane positioning has more weight than the V2X trilateration-based positioning. So in all, the scenarios worked well, but trilateration-based positioning is not performing so well as expected up to now. We are, together with Paolo and A22 team, we're trying to optimize this trilateration-based solution. So next steps, as said, we will investigate the V2X degraded modes in tunnel, and also we will optimize the trilateration-based positioning. Thank you. That's all.
Thank you so much, Filippo. And that was very interesting. And I really wish we had more time to also go more into detail. But we will be following the progress. And of course, we have regular updates on the website of PoDIUM in types of videos, interviews, papers. So, of course, you can always visit the website to get more information on this. Thank you all for your presentations. It was actually very, very interesting to listen to all of you. And now I will open the floor for the questions. As I mentioned in the beginning, you can use the Q&A box to type in your question and specify also the speaker or the topic where your question is addressed to. And as we give some time for the audience to type in their question, I have some questions for Guido, maybe for you, for use case 4, about the messages that you described. I think it's, or maybe you or Alessio, how do you define the messages types for the communication? What kind of criteria guided your selection for those? Is it, Guido, for you, a question for you, or Alessio?
Well, what I can say about the selection of the messages is that basically we wanted to stay on the standard. So we choose standard messages such as the EV message, because it's more suitable to use the structure of an EV message to give the type of information which was the time slot on which the pedestrian lane was free to perform the maneuver. So it was the most suitable message with this, and also because we will need to be compatible as possible. So we use these messages instead of maybe a custom message. Would be, yeah, it would be good to implement custom messages for VRUs and the crossings, but it would not be compatible with other vehicles. So we try to code this information in a standard already consolidated type of messages.
Okay, so compatibility also. I have a question. Maybe it's easy or it's hard to answer. If there is a traffic light violator, let's just say in that case of that scenario, how would that be classified in the system? Would that be an untrusted, let's say, user, untrusted data? And how would that be transmitted?
Well, the trusted condition of a user is more related with the communication point of view, since a trusted node would be a node which has been verified by the system or by the verifier part of the services of the PDI. The violator, the traffic light violator, such as a pedestrian that crosses with the red light, doesn't have anything to do with the trust or not trust condition. So it's only a communication. It belongs to the communication domain that allows a user to transmit messages or be used, these messages to be used into the PDI, and it doesn't regard the traffic behavior of the user. It's only a communication issue.
If I can add to what Guido is saying, I think this is important to say that the attestation mechanism does not, let's say, evaluate the user per se as a user and what it does at the intersection. It evaluates the communication entity. And that's very important also from law enforcement perspective. So it spots if there is a communication unit that communicates, let me say, garbage over the network, not a user. So it doesn't act by any means on a user or pedestrian that intends to violate. Of course, it gives a warning to everyone if there is a risk collision danger, but it doesn't enforce the code of conduct in the intersection. It's just to spot the misbehavior of the communication unit.
Okay, so it falls under the risk assessment. And that could be predicted, and it gets better as we go, correct?
Can you repeat, Sevi, please, the question?
Those kind of behaviors could be predicted better in the future, correct? In the risk assessment.
Well, the behavior can be detected currently. So traffic light violator might be detected because we know and detect the direction of a vehicle or a road user and the status of the traffic light. Of course, it might be heavy in terms of processing because a system should be continuously processing the traffic condition for every user in the cross point. So it is possible and it can be detected.
All right, super. There is a question coming in from Alexander Flucher. Could you be more specific about the CPM message version used in the single use cases, and if possible, extensions in PoDIUM? I don't know if you understood the question, if you would like me to repeat, or maybe I can open the microphone of Alexander so he can ask his question.
I think it's well understood. Maybe Guido, you have by heart the version of the CPM. We agreed maybe on the same version, right? To use.
Yeah, the version. Well, we have the version defined, but I don't have it here at hand. But it's written on the on the deliverables. But we can give you the precise version. We were not considering extensions because we wanted to keep the basic standard version of the messages.
Yeah.
So we can.
Yeah, I can also intervene. Also, I can't recall by heart the number of the version, but our choice that has been chosen in the use cases was between Stellantis and Lynx, because Lynx is providing the onboard unit for use case 4, and Stellantis is providing, based on Coda Wireless, an implementation in use case 5 by Stellantis. And in particular, in Stellantis, we are working not much in research, but in product development. So we are addressing those version of the standard that already are present in SDK of vendors. So that was the choice of the standard version was motivated by the presence of an SDK by the vendor that could enable us to start developing the product.
Alexander C. Thanks.
You're welcome, Alexander. Hi.
And we can share also in the follow-up article, together with the recording and the presentation, we can also share additional information, like deliverables where this kind of information could be detected. And keeping my eye on the time, maybe I can have another question for Alessio regarding the VIMA application that you've mentioned in your presentation. But just out of curiosity, are there any future developments you envision for the VIMA application, and how could it be involved to enhance an impact of this application, which was very, very interesting?
Yeah, well, thank you for the question. Well, actually, the VIMA is a service that only sends an alert if it detects a risk. But in the future, its functionality can be extended, for instance, by implementing an AI, which on the basis of historical data can run a dynamic algorithm that can send one or more messages depending on the condition, and then can allow the VIMA to evolve from a reaction algorithm to a prevention algorithm. For instance, it could alert an autonomous vehicle for the presence of an unaccepted event before the autonomous vehicle even encounters it, so that it can adopt appropriate strategy to deal with the event. For instance, slowing down the speed, or change the path for the autonomous vehicle. So yeah, in the future can be evolve the service to give other functionalities.
Super. Well, we'll keeping an eye on this. This is very interesting. Well, I cannot see any more questions coming in, and that means also we are finishing right on time, 3 minutes only over time. So I would say we can wrap the webinar here. I want to thank you all, Guido, Alessio, Paolo, Filippo, and Fabrizio. The presentations were really interesting. And yeah, with this, I would also want to thank you all for joining this webinar, and wish you a nice rest of the day.
Thank you.
Thank you.
Thank you.
Thank you.
Bye.
Thanks, everyone. Well done. Thank you.
Thank you all.
Goodbye.